Next, let's take a look at this third example problem. Charge A and charge B are 3 meters apart. Charge A is positive 2 coulombs, charge B is positive 3 coulombs. Charge C is located somewhere between them, and the force on charge C is 0. So how far from charge A is charge C? So let's first draw out where these charges are and the amounts of charge that they have. So first off, we have charge A. Charge A is positive and has a charge of positive 2 coulombs. Then we also have charge B, and charge B is likewise positive. It has a charge of positive 3 coulombs. And charge A and charge B are located a distance apart from each other equal to 3 meters. Then somewhere in between them, we have charge C. Charge C, we're not told if it's positive or negative, and what we want to find is the distance between charge A and charge C if the net force on C is 0. So I'm going to call this distance between A and C, I'm going to call that D, because that's the thing I want to find eventually. And if this distance is D and the entire distance between A and B is 3 meters, then this distance here between C and B would be equal to 3 meters minus D. Now I don't know what the charge on C is, but I also don't know if that matters. So let's look at the two scenarios, if C is positive or if C is negative. So first off, if C happens to be negative, so if C is negative, so we have a negative C, then what happens in that case? So if this is our C, if it's negative, if C is negative, then B is going to exert a force towards it. C will be attracted to B, and so the force of B on C is going to be in this direction. The force that A acts on with C is going to be towards A because C is negative. It'll be attracted towards A. So the force of A on C is going to be in the negative x direction. So these two forces are going to be opposite each other, and we just need to ensure that they're equal so that the net force on C is 0. So it should work out fine for C to be negative. What about if C is positive? So if C is positive, then if we have a positive C, then it will be repelled from B. B will push it away because they have the same charge, and so the force of B on C would be in this direction, but C would also be repelled from A. So the force of A on C would be in the positive x direction. So they would be opposite, and we would just need to ensure that the magnitudes are equal for the net force on C to be 0. So it looks like it doesn't matter if C is negative or C is positive. The strategy should be that as long as the amount of force from both charges acting on C, as long as they're equal in magnitude, then the forces on C will cancel. So let's do that. We need to ensure that the force of A on C is equal to the amount of force of B on C. And we can use Coulomb's law to ensure that that's true. So the amount of force that A exerts on C is going to be equal to Coulomb's constant times the amount of charge on A times the amount of charge on C, all divided by the distance between A and C, which we call D squared. And that's going to be equal to the Coulomb's constant times the amount of charge on B times the amount of charge on C, all divided by the distance, which is 3 meters minus D, and that also gets squared. So I think I can actually simplify this expression a little bit. If I have Coulomb's constant on both terms, so if I divide both sides of the equation by Coulomb's constant, that will cancel out. Likewise, I notice that I have Q sub C on both sides of the equation. So if I divide both sides by Q sub C, this amount, then that will also cancel. And that's awfully convenient because now it doesn't matter that I don't know how much charge is on C. So this equation then simplifies to the amount of charge on A. Well, let's see. The amount of charge on A is 2 coulombs divided by d squared. That's going to be equal to the amount of charge on B, which is positive 3 coulombs. So the amount of charge is 3 coulombs, and I divide by 3 meters minus d, and then that gets squared. So I just need to solve this equation for d, and then I will know how what the distance is of C from A. So if I solve this for d, let's see, I could imagine cross multiplying, and then I'll have this 3 meters minus d squared term. I'd have to FOIL that out, and if I did that, I would end up with a d squared term, a d term, 3 meters term. It really looks to me like I'm heading towards a quadratic equation. And as you know, there's a lot of math involved, and I think I want to be lazy here. And so what I'll do next is, it's kind of cheating in that if you do this, you're throwing away one of the 2 answers you get from the quadratic equation. And sometimes that's not the right thing to do. Sometimes that's the wrong thing to do, because the answer that you're throwing away may be the answer that you want. But I think what I'll do now is take that risk just to make the math simpler, and then look at the answer. If the answer I make doesn't, if the answer I get doesn't make sense, if d is negative or greater than 3 meters, I know I threw out the solution that was the one I wanted, and I have to go back and solve the full quadratic equation properly. But hopefully I won't get dinged too much for being lazy, and the solution that I threw out is like the negative one that I wasn't interested in anyway. So I'll take that risk and take the square root of both sides. So you can do this, but you should be aware that if you follow this approach, you are throwing away one of the solutions that the quadratic gives you, and it may be the one that makes sense for your problem. So it's a little bit of a risky thing to do. So if I do this, I see that I get square root of 2 coulombs, and then the square root of d squared is just d, and then that's going to be equal to the square root of 3 coulombs divided by 3 meters minus d. So now I won't get a quadratic equation from this one. So next, I think I'll cross multiply, and if I do that, I get d times the square root of 3 coulombs is equal to 3 meters minus d times the square root of 2 coulombs. And then I need to multiply this out over the parentheses, so d times the square root of 3 coulombs is equal to 3 meters times the square root of 2 coulombs minus d times the square root of 2 coulombs. And then I need to get everything with a d in it on the one side of the equation. So d times the square root of 3 coulombs plus d times the square root of 2 coulombs is equal to 3 meters times the square root of 2 coulombs. And then factor a d out of these 2 terms. So d times square root of 3 coulombs plus square root of 2 coulombs is equal to 3 meters times the square root of 2 coulombs. And then I need to divide both sides of the equation by the stuff in the parentheses. So that means d is going to be equal to 3 meters times the square root of 2 coulombs divided by the square root of 3 coulombs plus the square root of 2 coulombs. So if I do that math, put that into my calculator, I'm going to get a d that's equal to 1.35 meters. And if I look at my diagram in the problem statement, that does make sense. 1.35 meters makes sense for this diagram. It's not negative, and it's less than 3 meters, so that is the solution I want. So I did not suffer too bad a penalty from taking the square root here instead of doing the fully proper thing and solving the quadratic. So next, let's look at this question. Object A has a charge of +2 microcoulombs and object B has a charge of +6 microcoulombs. Which of the following statements is true about the forces between A and B?